in A and in B complement, or you could think of it as in A and not in B. So whichever one you kind of like better, right? So if I look at set A, that was 1 to 6. And so, well, let's look at B complement. If B is 2, 4, 6, 8, and our whole universe of everything, or omega, is 1 to 8, and B is 2, 4, 6, 8, write down what you think is B complement. In other words, not in B. So if B is 2, 4, 6, 8, what's left is 1, 3, 5, 7, right? For outside of B. And then this is an and, so it has to be in both. Because it's an and, it has to be in both. So what's in both of these? 1, not 2, 3, not 4, 5, and not 6, and not 7. So the set of things that is in A and not B in both is 1, 3, and 5. That's not a probability, that's a number, right? 3 things. So therefore, the probability of being in A and not B is there's 3 elements out of 8 total. And that one, of course, we can't use a union formula because it's not an or, it's an and, right? Okay, try C, and then I'll show you a couple crazy ones, okay? Okay, so this is in B and in A complement, or you can think of it as in B and not in A. Okay, so B was 2, 4, 6, 8, and we did A complement up above, right? It was 7 and 8. So it's an and, so I'm hoping you just looked at what was in both of them. 2 is not in both, 4 no, just 8, right, is in both. So therefore, the probability of being in B and not A is 1 number out of 8 numbers, or 1/8 total. Okay. So these ones are a little bit harder, right? So we've got still the same sets, but D says we want C complement and bracket A and B. Okay. So we did do A and B, or did we yet? Let's see. No, we did A and not B, right? Okay. So what's in both A and B? If I look at this and this, well, you write it down. What would be in A and B at the same time? So 2's in both, 4's in both, 6 is in both, guys. And what was set C? Because we haven't used it yet. Oh, I think I forgot to write set C down for you. Yeah, it looks like I accidentally didn't type it in for you. Sorry about that. So C is 3, 4, 5, and 7. Okay, so I want what is outside of C. So what would C complement be here, guys? Write your set. So that would be everything that's in the universe, but not C. So 3, 4, 5, 7 crossed out would be 1, 2, 6, and 8. Okay. Now let's take a look. We want this to be an and. So that means we need in both of these sets. So here's C complement, here's A and B, and we want what's in both of them at the same time. So what do you think? What would be in that set? C complement and A and B. Well, 2 is in both. 4, no. 1, no. 6 is in both. 8, no. So it's 2 and 6. So then remember I don't have enough room there. So remember the probability then of C complement and A and B is 2 elements out of, there was a total of 8, right? So 1/4. Now the next one, it looks very similar, but if you can notice what's the difference. This one's an or between them, right? So we have the set A and B, and we have the set C complement. So one way we could do it, we could say in C complement or in the set A and B, and of course, or both, but we just wouldn't write anything twice. So that's one possibility. So in one or in the other or in both. So take a look at your sets. C complement is 1, 2, 6, 8. A and B is 2, 4, 6. And basically we just write down all those numbers without repeating anything. So 1, 2, 6, 8 and 2, 4, 6, 8. So 1, 2, 4, 6, 8 then. So 5 elements, 5 numbers. So our probability of C complement union A and B would be 5 out of 8. Now, because it's a union, you could also use the union formula. So probability of not in C plus probability of A and B minus probability of not C and A and B. So if you take a look, how many was in each? Well, C complement had 4 elements and A and B had 3. So C complement had 4 out of 8, that one had 3 out of 8. And C complement and A and B, that was what we just did in part D, right? So this answer we have from part D. Otherwise, we'd have to do that too, right? And you may as well keep it as 8 because that way you can reduce your fraction easier. So 4, 7, 7 minus 2, so 5 eighths. Has to be the same answer unless you made a mistake, right? Because using a different method shouldn't, of course, change your answer. Okay, any questions about probability before we move on to the last section? You guys are almost done. Good job. Okay, so the biggest thing with conditional probability is making sure that you look for it and recognize it, okay? Because, people will often miss that it's asking you for something conditional. And of course, if you miss that, then you can't get it right because you won't use the right formula. So turn to page 134. 134. Okay. So conditional probability is finding the probability of something happening. What is the probability of something given that something else happened? Or if you know that this happened, what's the probability of, something else happening? And so the formula is probability of E slash F. The slash means given. So E given F is defined as the probability of E and F on top. And then it's all over the given one, which is the one after the slash F. Okay, so that's to find the probability of E, knowing that F has already occurred. And of course, you can use different variables. So for example, if we use A and B, and maybe we wanted, B given A here, then B given A would be, well, technically it's B and A, but the order is never going to matter, right? A and B, B and A, it's just the middle. So we can just call it A and B, and then over the given one, which is A. And when we draw trees to kind of, visualize, so some people don't draw trees for anything, but again, it's like a Venn diagram, right? Most people do learn better visually. So if you do, then you can draw one. You can only draw a tree if it's conditional, right? There has to be a conditional probability in order to draw a probability tree. But when we rearrange this and formula to find A and B, when we rearrange this formula, we would do this times this. And so it would be A times B given A to get A and B. And so that's why we say that, and is to multiply through the probability tree, because I'm rearranging this formula. I'm saying that A and B would be A times B given A. This A is the first branch of the tree, and then B given A will be your second branch on the right. Now, there's a couple of formulas that you should also learn. So complement rule. If you ever want the probability of not E given F, you can do 1 minus E given F. So if you do have E given F, then that makes that easy. The total law of probability. If you want the probability of E occurring, then you can do E given F1 times F1 plus E given F2 times F2. If there's EFG, you can do it for all of them and add them up. So I'll show you that from a tree. And we talked about these already. We said if they're independent, remember E given F is just E. E given not F is just E because E and F don't affect each other. So E given anything is just, going to be the E. Okay. And then F given E would just be F. F given E doesn't occur, etc. Okay. Okay, so Naveen performs an experiment in which E occurs 40% of the time. F occurs 30% of the time. E and F is 0.3. If event E occurred, what is the probability that F also occurred? So see this wording, if event E occurred, that's a given because they're telling us that E has already happened, right? So that is a given. So we have to make sure we get the order right. Because, for instance, if you find E given F and the question wanted F given E, of course, that's going to be the most common wrong answer that people accidentally pick. So we have to make sure that the if or the known or the given always goes second. It goes after the slash, right? The given part goes last, and what we actually want to find goes first. So this is asking us, if event E occurred, what is the probability F occurred? So what is the probability of F? We want to find probability of F given that E already happened. So that's F and E or E and F. Remember, it doesn't matter. Same thing for an and, just the middle. And then it's all over. This is where we could go wrong. The given one has to be on the bottom. So if we put F on the bottom, it's going to be wrong, right? It has to be the given one, which is E. So this is 0.4. And so we've got 0.3 over 0.4. Move the decimal twice. We just get 3/4, right? Or 0.75. Okay. Now in probability, they'll often give you numbers that you don't need, right? We didn't need that, right? Because they're not going to give you just what you need, or people have a better chance of guessing if they don't know what they're doing, right? So it's called a red herring, and they do it all the time in math, okay? Out of 100 people sitting at Krabby Joe's, 80 ordered nachos or ribs, 50 ordered ribs, 35 ordered nachos. What's the probability the person who ordered nachos also ordered ribs? So I'm going to go N for nachos, R for ribs, just to save us, writing. So let's see here. Nachos or ribs, so remember what that means in terms of your formulas and symbols. 50 ribs, 35 nachos. What is the probability a person who ordered nachos also ordered ribs? Okay, so remember, who ordered nachos also ordered ribs. So be careful. That's a given. Think about what is the given that they're actually asking us for. See if you can write it down. What do you think? So we want here a person who ordered nachos. That's what we know. That's the given or the known part. We know they ordered nachos, right? So that goes after the slash, and we want to know the probability that they want ribs. So this is what we want to find, and this is what we know or we're given, right? The person who ordered nachos also ordered ribs. We're given nachos. So write your conditional formula in terms of these symbols. What would be on the top and bottom here? So it would be R and N over N. Now we do know N, but we don't know R and N. So we're going to have to go down here and try and figure out how do we find R and N, right? Probability. Well, I hope you know how to find the and. We've done it so many times, right? We can use our union formula, right? They told us nachos or ribs, which is the union. So go ahead and write what's your nachos or ribs formula here. Write your union formula. And then you should be able to find your and to put it back into here. So have a go at it. Okay, so our union formula here, we've got probability of N plus R minus N and R. So if we fill out Well, the question clearly is conditional because read the question right here. What is the probability a person who ordered nachos also ordered ribs? So we went through the wording a few times. So you've got to be able to pick out the wording there, right? It does not say what's the probability they ordered both, nachos and ribs. Nowhere does it say that, so be careful. It says, what is the probability a person who ordered nachos also ordered ribs? So be careful. That's definitely 100% conditional. Okay, they're telling you they ordered the nachos. So really, 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 you have to read carefully. You may have to read it a couple times, right? Because if you miss the conditional, it's going to be wrong, right? It's very tricky, very tricky. Okay, so 80 out of 100 ordered the union, right? That was nachos or ribs, so that's on the left. 35 out of 100 was nachos, and 50 out of 100 was ribs. You're welcome. I know it's hard. It's a pain. So this is like 85 out of 100 minus what is 80 out of 100, right? 85 minus what is 80. So we would have just 5 then, right? Would be our and. So 5 out of 100. And I don't think I'll reduce it because then I think it will just be easier if I don't, right? I'll show you why in a sec. So now we have this formula. We can just stick them both in. So we have the and now. And we already knew nachos. Which one was nachos? 35, right? So now we can finally be done. To divide fractions, we would keep the top one the same and multiply by the flip or the reciprocal of the one on the bottom. So our answer is 5 out of 35. So that's why I didn't want to reduce the hundreds, because I needed to cancel. So 5 over 35, if I divide by 5, on the top and bottom is 1/7. So our final answer is 1/7, but we did have to do this part first, right? So it's kind of a, you know, I suppose this is like step 1 and then step 2, right? But you might not have figured out that you need another step until you did that. Okay. All right, so it's tricky. So anytime you have a probability question, you've got to ask yourself, is this a union? Is this a conditional, right? What do we have going on here? Okay. Questions? Okay. So for this one, it's also kind of a two-stepper. It gives me probability of E, probability of F, and E given F, and it wants F given E. So if I go to write F given E, well, could you write down what you think the formula is for F given E? F given E. So this would be F and E, which is really just E and F, over E, right? So we do know E. The issue is we don't know E and F. So that's why I had to then go back and say, well, I know this, and write that formula and do that first. So E given F would be E and F over F. And then because I know the given is 1/3, I can put that on this side and then find E and F, because I do also know F on the bottom. And to solve this equation here for E and F, using this and this, it would just be cross multiplying, right? This would be 1/3 times 1/4, which is 1 times 1 is 1 over 3 times 4 is 12. So now I can simply put that in and do the second part, okay? Okay, so it'd be 1 over 12 times 3 over 2, divide by fractions, flip the bottom one and multiply. So that'd be 3 over 24, which is 1 over 8. And, something like a tree here wouldn't help you because, if you go to draw a tree, E and not E, F and not F, from each of them, we know F given E, we're trying to find that, right? We get that to be 1/8, right? But we don't have any other givens, right? So we don't have any given probabilities here, right? And even if we drew it the other way, starting with F instead, then even if we drew this, then we have E given F. So this spot would be E given F, which is 1/3. But we don't know anything else, so it wouldn't help us, right? So too many unknowns, right, to use a tree. But I will show you when a tree will work, okay? But all of these second branches, in probability, all of the second branches are all conditional probabilities. They're all something given something, right? So in order to draw a tree, you have to have a bunch of givens. Okay, so let's do a few more examples here. Okay, university is made up of 70% students, 20% faculty, and the rest staff. So has to add to 100%. So 70, 20 is 90, so that's 10%. This past week, 80% of students, 60% of faculty, and 40% of staff went to Tim Hortons. Find the probability a randomly selected person went to Tim Hortons this past week, and then there's kind of another part down below, okay? All right, so I drew a tree just to show you what it looks like here. So we can have student, 70% are students, faculty, 20%, staff, 10%. And then I'm going to say T for Tim Hortons. And so what happens is a student can either go to Timmy's or not. T complement would be doesn't go to Timmy's. Faculty go to Timmy's or not. Timmy's or not. And these are givens because it says 80% of the students went to Timmy's. So, this probability right here, that's the probability you go to Timmy's given you're a student. Okay, those are givens that are told to you in the question. So this one, for example, that's the probability they don't go to Timmy's given that they're a staff member. Okay, now when you do probabilities, sets of branches have to add to 1. So this, and this have to add to 1. And then these branches have to add to 1, and add to 1. So they told me 80% of students, 60% of faculty, and 40% of staff went to Tim Hortons. So now I can say, well, if these add to 1, it has to be 80 and 20. These add to 1, it has to be 0.6, 0.4. And this is 0.4, it has to be 0.6. Okay? So all of the second branches here are all givens. Okay? All of the second branches on the right are conditional probabilities. Something given what's out in front, okay? So the question wants to know, find the probability a randomly selected person went to Tim Hortons. So that's not a given. It's not saying what's the probability went to Tim Hortons given it was a staff member or something like that. It's just a randomly selected person went to Timmy's. So that's not conditional. That is just asking us to look at our tree and find the probability that they went to Tim Hortons. Well, this is the law of total probability because there's different ways we can get somebody from Tim Hortons, right? We could have a student and they went to Tim Hortons. We could have a faculty member and they went to Tim Hortons, or a staff member and they went to Tim Hortons. And remember, is to multiply through our tree because we're rearranging the conditional formula, right? So remember this, to find the and, we multiply. So we want the probability that they are a student and went to Timmy's plus the probability that they're faculty and went to Timmy's plus the probability they're staff and went to Timmy's. So we have to multiply through, okay? So we take, this number is student and times by Timmy's given student, okay? And then we do this one, faculty times Timmy's given they're a faculty. And then this one, this number is the probability of being a staff member, right? Times, this is the probability they go to Timmy's given they're a staff member. Okay? Now, if this is just a multiple choice, of course, you don't have to do all of this, right? You can just think that, about what I said, and is to multiply through your tree, right? And is to multiply through your tree, right? So if we want, student and they went to Timmy's, we can just think, oh, multiply through the probability tree. Okay, so it's kind of up to you how much you need to do, like just depending on what your comfort level, I guess, is with everything, right? So personally, I would just say this, when I was doing it. And so I would just do this times this, plus this times this, plus this times this. So this would be 0.56, 7 times 8 plus 0.12. Be careful, this one only has 0.1 and 0.4, so that's not going to be 0.40, it's going to be 0.04, so just watch that. So 72%. Okay, so there's a part B. It says, find the probability a randomly selected person who went to Tim Hortons was a student. So now we are involving both things, right? Tim Hortons and then whether they were like, faculty, staff, or student. Okay, so read it again and see if you can figure out why it's a given. Find the probability a randomly selected person who went to Tim Hortons was a student. So who went to Tim Hortons was a student. So the who went to Tim Hortons is telling us that we know they went to Tim Hortons. That's the given. Find the probability a randomly selected student who went to Tim Hortons was a student. Who went to Tim Hortons was a student. We're trying to find the probability they're a student given we know they went to Timmy's. The given goes after the slash. The given is Timmy's, so T. Okay. So this is probability student and Timmy's over which one? Fill it in here. So that'd be the probability of going to Timmy's. Now, Timmy's we already have from part A, right? From part A, we did that already, so 0.72. So we just need to find student and Timmy's. Student and went to Timmy's. Well, again, we know and is to multiply through, so student and Timmy's would be right there. 0.7 times 0.8. And that would be 0.56 over 0.72. So you could just, get rid of the decimals and say 56 over 72. Which if I divide by 8 is 7/9. Now, if you didn't have part A and you had to do it directly, you would still have the same thing on the top, and you would still have this on the bottom. I just want to point out one thing to you about this. When you take a look at this, just make sure you don't ever think you can cancel something, okay? They'll never, ever, ever be canceling because these are all plus. So just so you know, don't see that and think, oh, I can simplify something, because you can't, okay? So just be aware of that. Okay, any questions? Okay. So if they ask you a conditional one about something like a dice, you can, use the formula, but it's very complicated. It's a lot of work. So what I would do if I had something like rolling a die and they want you to, find something conditional, like here, find the probability the sum of the numbers is greater than 9, given that the first number shows a 4, I would just do what's called reducing my sample space. Reducing, of course, means make it smaller. So we know that normally there's 36 outcomes. But if I say that I'm given the first die as a 4, then guess what? I only have, I don't have any of those, I don't have any of those. I only get, the first die is a 4, I only have the choice of those, right? So instead of thinking of 36 outcomes, I'll only think about the ones where the first die is a 4, because they're telling me I'm given the first die shows a 4. So then of these 6 outcomes, what I want is the probability that the sum is greater than 9. So then I'm just going to circle anything that satisfies the condition of greater than 9, right? So 4 plus 1 is 5. That's not greater than 9. 4 plus 2 is 6. No. 7, 8. No. So greater than 9 is only one case, right? If it was greater than 8, then it would be 9 or 10. It would be 2 cases. But yeah, greater than 9, just one case out of 6, okay? Now, if they try and do something tricky, so one time they gave them one that didn't really have anything. So if you're given the second die as a 1, then if the second die is a 1, it's 1, 1, 2, 1, 3, 1, all the way up to 6, 1. But then it says the sum is greater than 9. Well, what's the issue here, guys? Are any of them greater than 9? No, right? So that's just mean, right? So there are 6 cases, but 0 are greater than 9. So the answer is 0. Okay. All right. So if HIV has a prevalence of 3% in San Francisco, and a particular HIV test has a false positive rate 0.001 and a false negative rate of 0.01, find the probability a randomly selected person will test positive. Okay. So you can either have a disease or not have a disease. And then your test can be right or wrong. So if you have the disease and it tests positive, then it's the right, answer, which we'll talk about for the final. We'll talk about type 1 and 2 errors. But for now, you can have a disease and the test is positive or negative, and you cannot have the disease and the test is positive or negative. Okay, so I'm using T plus is the test is positive, and T minus is your test is negative. Okay, and then these D's, D plus means you have the disease, so you actually do have it, and D minus means that you don't have this particular disease. It could be any disease. I mean, this one says HIV, but it could be anything on the exam. So a tree can help us kind of visualize what's going on. So it says 3% have HIV. So that's have the disease. So that I can put there. Remember, our branches add to 1. That means 97% don't. And then it tells me false positive 0.001. So that means it tells me I have it, but I don't, right? So it tells me I have it, but I don't have it. And then a false negative means it tests negative, but I have it. Okay? So, false positive test says you have it, but you don't. So, if your branches have to add to 1, that's 0.99, and that's 0.999. So the question is, what is the probability that a randomly selected person, so if I select somebody at random, that they will test positive? So this is, again, the law of total probability, because we can test positive in more than one place. We could have the disease and get a positive test, or unfortunately, we could not have the disease and it tells us that we have, we have a positive test, tells us we have it, right? So this is, again, if something occurs at the far right of our tree, we have to multiply through to get to it, because we really want have the disease and test positive. Don't have the disease and test positive. So again, it's and, which is multiplying through. Okay, so positive disease and test positive right here. And again, multiply through the tree. You can also think, anytime you want something at the far right, multiply through. Okay. Okay, and then other case, so or, multiply through here, 0.97 times 0.001. Put the decimals in because they were kind of annoying. Just time-wise, so you wouldn't have to fool around with them. But make sure you practice everything that's on an exam without a calculator, just in case, okay? So I don't know how good you are with decimals, but some people are better with decimals, some people are better with fractions, so I kind of put both. Okay? But this one wasn't conditional. So you do have to pick out what is and what isn't. Okay. So suppose Alex has 70 red, 30 blue. Samuel has 50 red, 50 blue. Benjamin has 45 red, 55 blue. Pick a boy at random. What's the probability of picking a blue? Okay, what would your tree look like here, guys? So we could have Alex, Samuel, or Benjamin, right? So if Alex gets picked, or Samuel, or Benjamin, and since they say we pick a boy at random, they're all equally likely. So all their probabilities are the same. So 3 of them would be a third, there's 4 of them be a quarter, etc. And then we have, let's just use R for red. and B for blue. Okay, so fill it in and write down what do you think the probability is that you pick a blue if you're just picking somebody at random. Okay, so if we have, what is it, 70 and 30, so there's 100, right? So 70 out of 100, may as well just say 7/10 and 3/10 then, right? And here, 50 and 50 would be a half and a half. Maybe we should just leave them as all over tenths though, right? Because it might be easier. And then, maybe that's not going to work for tenths. So 45 and 55. So I guess the best we can do with that, let's see, if we divide by 5, we could say 11 out of 20 and 9 out of 20. Okay, so we want the probability that we pick a blue. So blue, again, is at the far right. We know that these are all conditional. So in other words, you know, this is the probability that you pull out a red given you picked from Benjamin, right? Something like that. So to get blue, anything at the far right, we've got to multiply through to find it, right? So we've got to find the probability that we picked from Alex and we got blue, plus that we picked from Samuel and we got blue, or plus Benjamin and blue. Okay, so multiply through all the ways to get to blue, the law of total probability. So we have a third times 3/10 plus a third times 5/10 plus a third times 11 over 20. So common denominator, so I guess we could convert them. Well, this is 3 over 30 plus 5 over 30 plus 11 over 60. So do 60th. So add them up and see what you get here. So if I times by 2, I get 6 over 60 plus 10 over 60 plus 11. So 16, 26. So 27 out of 60. We could divide by 3 and say 9 over 20. Or if you want the decimal, that's like 4.5 out of 10. So that's just going to be 0.45. Could also convert it to hundredths to get the decimal as well. Okay, so for part B, what is the probability if you got a blue marble, then it came from Samuel's box. Okay, write down what you think that's asking you. If you got a blue marble, that it came from Samuel's box. So if we got a blue, that's the given, right? They're telling me it was blue. The given goes after the slash, and we want to know the probability that came from Samuel. So we're trying to find Samuel given that we know we got a blue. Okay, write down your formula. So it would be Samuel and blue marble all over the given one, which is blue. So if we didn't have part A, we'd have to do blue, wouldn't we? And we'd have to do all the ways to get blue, multiply through, add them all up. Because we have it, we're kind of lucky that way, right? And the top is Samuel and blue. So go ahead, look at your tree. Which part is Samuel and blue? It's going to be right here, right? So 1/3 times 5/10. And remember, you could never ever cancel anything. So if you had to do the whole bottom, you wouldn't be able to cancel anything ever, okay? So that's what? 5/30 divided by this would be times the reciprocal. So we may as well cancel the zeros. So 5 times 2 is 10/27. Okay, any questions? Okay. Suppose that among those with head injuries, 5% have skull fractures. Okay, so let's use S for having a skull fracture. And nausea, so I'll say N, occurs 95% of the time when a fracture is present. When a fracture is not present, nausea only occurs 80% of the time. What is the probability a patient is not nauseous after a head injury? Okay, if you use S for skull fracture, N for nausea, draw out your tree here, what it would be. So we can have a skull fracture or not. And then after skull fracture, we can have nausea or no nausea. Right? So this is nausea, and any of the N complements are, they don't have nausea. Remember, these are all conditional, right? Or givens, right? So 5% have skull fractures. So that's here. So fill in the number below. Add to 1, so 0.95. Nausea occurs 95% of the time when a fracture is present. So 95% goes here. This is the probability that you have nausea given you got a skull fracture. Remember, these are all givens. Something given what's in front. And then this would have to add to 1. So if that's 95, that's 0.5. And then down at the bottom, it says when there is no skull fracture, nausea is 80% of the time. Okay, so fill that one in. So 80% of the time we get nausea. So remember, this is the probability of being nauseous given you didn't get a skull fracture. So that's 0.2. Add to 1, add to 1, add to 1. Okay, is part A conditional? What is the probability a patient is not nauseous after a head injury? Well, the whole tree is about head injuries. So not nauseous. It doesn't say not nauseous given a skull fracture or skull fracture given they weren't nauseous. It just says they're not nauseous. So that's not conditional. That's just N complement. Now, N complement, though, does occur at the far right of your tree. So write down what you're going to do here. What do you think it would be? Well, it's at the far right, so we'd have to multiply through, wouldn't we? Right? We'd have to do all the ways to get to not nauseous. So we could do S and N complement, or other case, not S and N complement. And remember, the ands are to multiply through our tree. Okay, so write down what your answer would be here. So I'd have 0.05 times 0.05 plus 0.95 times 0.2. And if you don't like the decimals, you could also use fractions. So 5 over 100 times 5 over 100 plus 95 over 100 times 20 over 100. So that would be 25 plus, well, 95 times 10 would be 950. So 95 times 20 would be 950 and 950. So 1900. So our answer would be 1925 over 100 times 100. So 10,000. Or you could say 0.1925 if you wanted a decimal. Now part B. What is the probability of no skull fracture given that a person has nausea? What is the probability of no skull fracture given they have nausea? So we can't just do that from the tree, right? Because this is nausea given skull fracture. It's not the right order. So you can do it directly. You can do S complement and N over N, or you can use this formula and say it's 1 minus S given N. Okay, so either one is fine. So when you want to find S complement given N, it's either this or this. So whatever you prefer. And you'll just write this one out. So this would be S and N over N. And S and N we'd have to get from the top, right? So S and N would be here, right? Skull fracture and nauseous, so 0.05 times 0.95. Now we could do nausea directly from our tree, right? Just like we did no nausea in part A, like we could do all the ways to get to N, multiply through here, add them up. But because there's only two things going on, either you are nauseous or you're not, and we have the total for not, we could do, 1 minus what we got for not nauseous, and that will be the same for, what your probability is of being nauseous. Okay. So one more quick thing, okay? Almost done. So for genetics, sometimes they talk about, Punnett squares, and so you can draw them out. So for example, if we're looking at pea plants, we can have purple or white. So capital F is the allele for purple, and little f is the allele for white. And of course, the genotypes are, big F, little f, or big F, little f. And these two are called homozygous. Remember, they only carry the same allele, but if they're mixed, then we call it heterozygous. And if they have any kind of dominant, capital F, then they would look purple. And because purple is dominant, and a little f, so there's no big F, then it would look white. So this one here, we've got little y is crossed with big Y, little y, right? So this shows you the combinations, right? We can get big and little here, this one, big and little, and here, little and little. So what is the probability of an offspring being, in this case, these are pea plants, so it was yellow and green. So here, we have that this and that would be yellow, and little would be green. So let's see, we want to know what's the probability that they would be green. Well, which ones would look green here? Well, it'd be half, I guess, because those would both be green. So it'd be 2 out of 4, or 1/2. And these two each have a capital and a lowercase, right? So dominant and recessive. So those would both look yellow. Okay, well, I hope you learned a lot. So study really hard. Maybe go take a nap before you do a bunch of math all day. So enjoy a little bit of time, hopefully having a rest before Monday. And yeah, tell your friends to sign up. And I hope it goes really well for you. And hopefully I'll see you for the final, okay? And you just email me any questions that you have, okay? So good luck, everyone, and do all those practice exams too, okay? All right, hang on if you have any questions. Thanks, guys. You're welcome, Charlie. Thanks for saying thank you. Okay, any questions? You're welcome, Hannah. Thanks. Yeah, so like in that question where they said, playing on the swings or playing on the slide. So when you see or, in the form of probability, then or will always mean a union. It'll mean in one or the other or both. So always think union language, like for probability for math questions, not what you kind of think about in the English language. We kind of tend to say if you're in, playing on the swings or the slide, you're only doing one or the other, right? Yeah. That makes sense? You're welcome. Good luck. I hope it goes really well. Okay, does anyone else have any questions?